Okay. Yes, let's start our class. Sorry for being late. All right, and then people from Zoom, I am already starting recording, just so you know. And you should be able to see my screen from your end as well. If everything looks great, I am going to start. So today we are going to, talk about a new kind of vulnerability. You may notice that we don't have a video posted this week. So today I am going to actually having this in-person lecture talking about these new types of vulnerabilities. And then we're gonna have a lab based on, today's content. And today we're gonna talk about Fastbins. So in previous weeks, we mentioned, we talk about T-cache, and we spend, I think 2 or maybe 3 weeks that talk about like T-cache structure in different kinds of vulnerabilities, right? Such as use after free, double free, and overflow, right? So T-cache is just one of the data structure in the heap, right? So if you watch the videos from last week, you know that there are also other data structures such as Fastbins, small bin, assorted bins, like all different kinds of data structure. And in fact, T-cache is perhaps the youngest data structure, introduced since the GDP's 2.27. So this is like a new data structure that is specific designed for performance boost. Before that, there are other beans, there are other data structures that supports efficient dynamic memory allocation. And that's why the other beans, they all exist, and there are actually already existed for a long while. So, and then this doesn't mean that they're not vulnerable. I mean, they're also vulnerable. So if you look at the categories, it's like there are these 3 kinds of vulnerabilities. And then these 3 kinds of vulnerabilities, actually it can occur on other data structures as well. So beyond the T-cache, there are also other beans that can suffer from this kind of vulnerabilities. And then based on those different kinds of vulnerabilities with, occurred on different kinds of data structure, we will have different types of attack. So those attacks that we talk about in previous, weeks, those are about T-cache. And then today we're going to tackle Fastbin. We're going to talk about other possible attacks that leverage those vulnerabilities that potentially can occur on Fastbin. And in this week and today specifically, we're going to talk about use of the free on Fastbin, and we're going to talk about how we can leverage or demonstrate this kind of vulnerability on this kind of data structure using the attack that we're going to talk about in a few minutes. Okay. So yeah, again, outline, we're going to talk about Fastbin's use of the free vulnerabilities today. And then, we will talk about Fastbin double free vulnerabilities in next week. And those attacks that we're going to talk about can be categorized as Fastbin reverse. Okay. I will talk about like why it's called Fastbin reverse. Actually, you will notice that later on. There is like kind of a reverse order inherited with attack, and then you will get to know that later on when I talk about that. And besides that, we will mention how to leak libc address based on the vulnerabilities, and also like how to debug. But those are the like future topics that we will cover. So today we're gonna mostly tackle the first one, Fastbin use of the free vulnerabilities and attacks. Okay. So, we have talked about T-cache bin, right? And then in last week's video, we also touched a little bit about the layout of Fastbin. So if you can recall, the layout of Fastbin's free list is slightly different from the one in T-cache bin's free list. And the difference here is the arrow. Like you see that the Tcache bean has this the blue arrow, like I show it in blue, and Fastbin has this red arrow. So the reason why I differentiate these two arrows is because the place that this pointer is pointing to is different, right? So you see here, so every chunk has metadata and the actual data, right? And also it has the FD pointer, which is the forward pointer, which will point to the next free chunk. So for memory chunk, when they're under use, there is no forward pointer. So when it is under use, the actual data will be stored right after the metadata. And the metadata is 16 bytes. We showed it in previous slides, like, in the 16 bytes, there are some flags. There are also, a few that represent the size of the chunk, right? Okay, so when the chunk is under use, there's no forward pointer because, again, this chunk is not in free list. So it's not belong to any of the list, so that it doesn't need to point to the next free chunk in the list, right? However, if the chunk is currently being freed, means that this chunk is ready to be reallocated in the future, then this free chunk will reside in a Tcache bean or Fastbin or other kind of beans free list, meaning that this chunk can be reused, right? And as long as it's in the list, you need to specify what's the next element in this list, right? And if it's okay that the chunk is the end of the list, but still, like, if this chunk is not in the end of the list, you need to specify, where is the next element. And if the chunk is in the end of the list, then you want to show that, okay, I am the end of the list, right? So you want to specify that this is the end of the list. So that's why the forward pointer information is necessary, for a freed chunk. And the way that the libc is designed is that they put the forward pointer as the start of the data, the original data field. Does it make sense? Okay, cool, awesome. Okay, so then for Tcache bean and the Fastbin, the forward pointer will point to a different location. It will all point to the next chunk. It's just the address that is associated with the next chunk will be different. So for Tcache bean, it will point to the start of the data, right? So it's like the starting of the address that is next to the metadata of a chunk. So it's like the actual start of the data, the start of the actual data resided in a freed chunk. And then on the contrary, for Fastbin, the pointer will point to the start of the chunk instead of the start of the data. Does it make sense? Good, cool. Yeah, so, that's, yeah, question, yeah. Can you be louder? Sorry. Yeah. Well, yes and no. Yes, it points to the next forward pointer, but also the next forward pointer is at the start of the data. Does it make sense? Yeah, because, that's why I was saying, like, when this chunk is under use, you don't need a forward pointer, right? So that you can use that location to store data. Yeah. Okay, so I'm just gonna repeat this question because I don't think that Zoom people can hear that, it's just a little bit too distant. But so the question is that, is it true that in Tcache bean, the forward pointer will point to the next forward pointer instead of the data? And then the answer is yes and no, because yes, it points to the next forward pointer, but no, it still points to the start of the data because the forward pointer is at the start of the data. Like, they're gonna share the same address. Okay, good. All right, so this is the way, or say this is the difference between Fastbin and the Tcache bin. And you may wonder why, right? Like why they designed in a different way. And the answer is performance. It's just like the next time, like or say by the time that glibc designs Tcache bin, they want to optimize the performance. And they realize that, okay, in order to optimize the performance, we don't really have to make forward pointer to point to the start of the chunk. We only need forward pointer to point to the start of the data, because you know that every time when you call malloc, what is returned from the malloc is the start of data, right? And then because of that, by the time they designed Tcache bin, they determined to make forward pointer to point to the start of data. And of course, they cannot change Fastbin because they want to make sure that the future libraries are still gonna be compatible, to previous versions. So that's why they remain Fastbin is there. And in the meanwhile, they create a new data structure, Tcache bin, and with a better performance by designing the forward pointer in this way. Okay, cool. Okay. And this difference is important because when we develop our attack, we need to be a little bit careful. We need to make sure that in the future, if we want to overwrite, the forward pointer, change that with some value, we should change that value to become, something that is relevant to victim memory, but not exact victim memory, because we have to make sure that the chunk that we created here will point to somewhere ahead of the actual victim memory, which I will show you later on if you don't understand what I'm talking about right now. Okay. Okay, cool. All right. So now let's talk about a Fastbin used after free. So if you remember Tcache bin, the way that it works is that we build a hypothetical chunk there, right? Like a victim. And then we let a freed chunk. We added a freed chunk, the forward pointer of the freed chunk, to let it point to a victim place, right? So that later on, when we call malloc, that victim free chunk will be returned back to you, and then you can start to do arbitrary read and write, and then later you can transfer that from arbitrary read and write to an arbitrary execution, right? So this is like high level how Tcache is used after free works. And then similarly, we want to do, we want to kind of leverage, if we want to leverage the use after free on Fastbin, we're going to add a freed chunk in Fastbin, and then edit it in the way that we want to let a freed chunk, to point to a hypothetical chunk. We call it a fake chunk, right? So that in the future, if we do malloc, like if we call malloc again, this fake chunk will be considered as an available chunk that we can get back from malloc. And then we can start to access this victim location. Does it make sense at this point? Good. Okay, cool. And also keep in mind that right now, because of Fastbin, we have to change this forward pointer to point to, a fake chunk, which starts with a hypothetical metadata, followed by the victim location, like the victim data that we can add it. So that's why I emphasize that the difference between, Tcache and Fastbin is that the pointer is different. So previously, we changed the forward pointer to point to the start of data, but now we have to rewrite the forward pointer to point to somewhere ahead of victim, which will include a hypothetical metadata. Okay, good, makes sense? Awesome. All right, so now let's start to talk about like the process, how that works, okay? So the first step for us is to identify is to identify a so-called fake chunk. So this chunk will contain a so-called metadata, right? And a so-called data field. And in this data field, the start of it will be treated as a forward pointer, right? Because by the time that this fake chunk is linked to the Fastbin's free list, this chunk will be considered as a freed chunk, and it must contain a forward pointer's information. Okay. And then because of that, because the fake chunk will be considered as a freed chunk, there is a specific requirement in terms of the forward pointer, the hypothetical forward pointer in this fake chunk, which is that this pointer has to be either equal to 0, meaning that, okay, this is the end of the current free list, or it has to become a legitimate forward pointer's value. And if you don't understand what I'm talking about right now, like what does it mean by forward pointer equal to 0 or something else, it's okay. We will demonstrate and we will repeat this again later on when I talk about this allocation process. Okay, like memory allocation process. All right, so now just like you can keep in mind that when we find a fake chunk from the memory, there has to be an extra condition needs to be met by this fake chunk. So it's not like any chunk or any memory location will be available to be treated as a fake chunk. All right. Okay, so then the next step will be, let's edit a freed chunk from Fastbin's free list so that it will point to the fake chunk, right? And then the next is that suppose that we already have a fake chunk, then we want to obtain this fake chunk by calling malloc for multiple times, right? So we want to make sure that we can get this fake chunk by calling malloc. After some time, the malloc will return us with this fake chunk, and then we can access it. So this is similar to Tcache. However, the difference is that because Fastbin, like the way that the glibc works in terms of memory allocation is, is different to Fastbin, contrary to Tcache. We need to be careful when we do malloc. And if you remember in last week, we talked about glibc's mallocing, like memory allocating process. Like they have like kind of a priority list. Like Tcache bean will be the first beans that will be like prioritized, saying that it means that if there is a chunk to be freed, then that free chunk will go to Tcache bean first if there is still empty room from Tcache bean. So Tcache bean can only hold up to 7 chunks within the same size, right? If you remember last week's video. So that's why that like whenever there is a chunk being freed, it will first be put to Tcache bean if there's room available. And if there's no room available there, it will then put into Fastbin. So it's like Fastbin is the second choice. If the first choice is not available, glibc will go to the second choice. And also similarly, if a malloc being called, like if the program calls malloc, then glibc will first look at Tcache bean and then see if there is any chunk available. And if there is chunk available for that malloc, it will return that chunk to malloc. And however, if there is no chunk available there, it will then goes to Fastbin. Okay, so that's the reason why if we want to, get this hypothetical fake chunk, and if there are already some of, the chunks currently available in Tcache bean, the first thing that we want to do is we want to deplete Tcache bean. We want to, using malloc, we want to get out all the current freed available chunks from Tcache bin. Okay, does it make sense? Good. Okay, cool. So that's why, you know, I have this malloc times 7 here. It just means that, okay, if currently we have 7 chunks in Tcache bin, then we want to first deplete Tcache bin. You know, by depleting it, I mean, we need to call malloc for multiple times so that all the chunks in Tcache bin will be retrieved. Okay. All right. So now let's talk about the next step. Suppose that we already deplete Tcache bin, so there's nothing there, and in the meanwhile, there are, you know, Fastbin's free list available with our hypothetical fake chunk. Okay. So now I want you to be a little bit careful in this case, because the way that glibc work is a little bit complicated at this point. So by the time that the malloc is called again, okay, by the time that malloc is called again at this stage, glibc will do 2 work, like 2 steps. One is that it will first return the current first chunk in Fastbin to the malloc. Okay, so that's step number 1, but this is not over. The next step is that glibc will move the rest of the chunks from Fastbin to Tcache bin. And then we call it like Tcache bin refueling. Because glibc, for the matters performance, they believe that if you are calling Fastbin or if you are calling malloc with this size, then it's likely that you will ask for more similar chunks. You will ask for more chunks with the same size in the future. So that's why they want to move those available chunks from Fastbin to Tcache bin, so that in the future, if you call malloc again, it will return you the chunk in a more, you know, in a faster way. Because keep in mind that Tcache bin has a better performance than Fastbin. Okay, does it make sense right now? Okay, good. Yes, question, yeah. Mm-hmm. Yeah. So if Tcache bin is not completely allocated, then Fastbin will not going to be used. It will go back to this situation. So if Tcache bin is completely allocated, then it will go to this case, right? Yes. So I'm trying to understand your question. So you said that, you know, yes, glibc will prefer Tcache bin over Fastbin. Yeah. And right now Tcache bin is depleted, right? So there's not available. Yes. So that's why glibc will go for Fastbin, because there's no choice from Tcache bin at all, right? So as long as there is a choice in Tcache bin, glibc will always go for Tcache bin. Does it make sense? Yeah. Mm-hmm.
When we are choosing similar size blocks,
yeah.
Is that after we have repeated Tcache bin or?
Oh no, it's all the time.
Okay.
Yeah, it's all the time. Yeah. So it's not like after Tcache bin was depleted. It's like all the time. So that means that as long as there is a chunk available in Tcache bin. Right. Yeah, yes. Yes, exactly. Yes. So yeah, if there is no chunks in Tcache bin, then glibc will use Fastbin. Otherwise, glibc will always use Tcache bin. Yeah. All right. Okay, so let's continue now. So as I said, like the way that the way that glibc works is that it will use the first chunk in Fastbin and then return and like use that as the returned chunk for the current malloc. But then the next is that along with that returning, like it's not going to be the end of this operation, this malloc. Again, the next that glibc is going to do is that it will move all the chunks to Tcache bin. Okay, because again, or when I say he means that glibc thinks that it might be users may keep asking for more chunks in the similar size, in the same size in the future. Okay, so because of that, the way that glibc moves those, those chunks to Tcache bin is that it will start with the current first chunk, right? And then move it to Tcache bin, append it to Tcache bin's free list, and then always insert the chunk to the start of the free list. And then that's why I call it reverse. Because if you look at the order right now, previously the fake chunk that we put there was the first element in this current list, right? But then after this movement, you will realize that the fake chunk will become the last element in Tcache bin. So the order of the fake chunk will be changed. It will be reversed actually, right? So that's why we call it Fastbin reverse attacks, okay? And this explains why we have to, find a fake chunk in a proper way, meaning that we need to find a fake chunk that satisfies that the forward pointer field in this fake chunk has to be legitimate. Because if the forward pointer, the forward pointer can be equal to 0, okay? Or it can be, another pointer that points to, some other possible places. But then ultimately, we have, another chunk that maybe ends with 0. Because the reason why for that is that we want to make sure that by the time glibc moves those chunks, everything will work smoothly. Because the way that glibc works is that it will access this current chunk, okay? And then they know this, like when I say access this, it means that it will has a pointer, right? That contains the address of this current fake chunk, right? And then it will move this address, copy that address to free list, right? So that in this case, the free list will point to this chunk. And then using that black pointer, it will read the forward pointer value. So that it means that it will actually point to the next chunk, right? So if the forward pointer value here is not legitimate, for example, the forward pointer has a value of say hex 1, right? And then the pointer, this pointer will have a dereference error because it will always use this information to find the next available chunk. All right. Yeah, question. Search it again. Yes, Tcache has 7. Yes. Yeah. Yeah. So there are two things. One is that if Tcache already have 7 chunks there available, right? Then they were not gonna insert the 8th slot, the 8th chunk, because Tcache can only hold 7. I mean, in this case, Tcache is empty, right?
So if it's done again, it continues up until the past. It doesn't go to the detection. It goes to the gate only to the detection.
Yes, yes. Yeah, so if there is still, chunks available here, they will first make this like this empty. So that this being said, gdlibc will not going to move those chunks to Tcache bin if Tcache bin is not empty, basically, right? But also another thing is that if there are many items in Fastbin, say there is 100 items, then they're not gonna move all the 100 items to Tcache bin. They're only going to move the first 7 items in Tcache bin because Tcache bin can only afford 7 items, okay? And then, again, when malloc was called, besides returning this current chunk back to malloc, it will move the first 7 items to Tcache bin, right? And then the forward pointer has to be legitimate so that it can finish this 7 chunk movement. And then when I say legitimate, it means that this forward pointer has to point to somewhere which will not cause dereference error, right? Yes, question. Yeah. Yeah, good. So the question is that by the time that malloc or glibc moves the 7 chunks to Tcache bin, is that the first 7 or the last 7? And the answer is first 7. And the reason for that is, again, performance. So think about this. If you have a list, right? And then you want to access the list, like accessing the first 7 list is going to cost you less time than accessing the last 7 list, right? Because it's a list, there's no way that you can index it. You have to access it all the way from the beginning. So that's why they only use the first 7. And also similarly, the reason why they append or like they move the 7 chunks to Tcache in a reverse order is also because of performance. So think about this. If you have to move this in the same order, then what you have to do is that you have this, right? And then after you move, then you have to append this chunk to this current chunk. But then in order to do that, you have to have another pointer that points to the forward pointer, right? And then you have to have another pointer that always move to the end of the current list so that append the next one. But then that will cost extra time because you have to always maintain an actual pointer that points to the end of the list. However, if you always just insert it at the start of the free list, you know that Tcache bin will always store that anyway. So you don't have to maintain another list tail pointer. Does it make sense? Yes, question.
I'm getting the last letter.
Yeah. So the question is, how about the performance look like if we use the last 7 chunks from the Fastbin, right? Is that your question?
Yeah, I'm getting
Oh, I see what you're saying. So you're asking that what if when we, do this reverse, we do the reverse of the reverse, right? Like it's like we go to say the 7th chunk in the Fastbin first, and then we move that we move that to the start of the Tcache bin, right? But then you will still waste like kind of 7 access because you now need to access the 7th chunk by move your pointer, right? So you don't want to do that, right? Because it's a cost of performance. So that's why they sacrifice the order, which they don't really matter. I mean, it doesn't really matter for glibc, right? They don't care which chunk is going to be reallocated or reused first. And they want to have the best performance. So that's why they always want to use the first available chunk in Fastbin and then move that to the Tcache bin, not starting from the 7th. Make sense? Cool. All right. So yeah, this is how it works. So after that, like after this movement, the Tcache bin will look like in this way, right? So it's like if your fake chunk's forward pointer is not 0, then it will become, the fake chunk become the last element, and then there will be some other, chunks there. And if at the beginning your forward pointer of your fake chunk is already 0, then this will become the only, chunk that is available in T-cache. So I'm just like list 2 possibilities, right? Because one is that if the forward pointer is not 0, then it's gonna be like this, right? Like this situation, and everything will be reversed in T-cache. And if you have make the forward pointer of your fake chunk equal to 0, that means that there's no these 2 elements or no more elements appended after the chunk. So that's why the T-cache will only contain 1 fake chunk. Yes, question. Okay. Yeah. Okay, I see. That's a typo. Good catch. Yeah, there was no reason. So the question is that why is this pointer points to the middle of the chunk, not the start of the chunk? Yeah, so this is a very good catch. It shouldn't be like this, and this is a mistake. Let me correct it right now. Oops. Okay, very good catch. Awesome. Yeah. Okay, so now let's talk about the fake chunk, because now you start to understand why at the beginning, in the first step, I told you that you need to find a legitimate fake chunk. Turns out that, for many times, if you use, say, malloc, like God table, right? Like in previous T-cache, we use God table. God table may not work, for Fastbin's attack, because the malloc table, like usually they're just items by items, right? That means that there might be another, entry in God table that, has some values there which cannot become the metadata or not become the forward pointer. So for example, if the malloc, at the God table currently has some value like ABCD, like something like that, then it cannot be used as a fake pointer, fake chunk, because the forward pointer's value will be equal to ABCD, and it cannot be dereferenced correctly, right? So, and then because of that, we want to find another possible place or another safer place that we can use with legitimate hypothetical forward pointer. And one possible chunk or one possible data field that we can use is called malloc hook. Okay, so malloc hook is a symbol in glibc, and it's actually in the data segment of glibc. So if you use like VMM map or cat the process memory layout, normally you will see like multiple items that representing glibc, right? So one part is the code and the other part is data. And this guy is in the data part of glibc. And the reason why malloc hook is there is that glibc supports a user specified extension in a way that if malloc was called, glibc will first look at the malloc hook and then see if it contains some value that points to a function. So that's why they call it malloc hook. Basically, user can hook glibc's malloc to do something else or to implement their own malloc. Okay, And then because of this nice support, an attacker can leverage it by rewriting malloc hook, to replace that or to override the malloc hook with, say, function wing or like any of the places that we can do arbitrary execution. And normally malloc hook without any specifying is going to be equal to 0, which is fantastic as a forward pointer, right? Because it just means that this current fake chunk is the end of the list. Does it make sense? Yes? Okay, good. And then besides malloc hook, we can also use free hook or realloc hook. And in order to find this field, you could use opstomp -t, like capitalize the T, which is to access the symbol from glibc. And then you can just then search malloc hook or free hook or realloc hook to identify the offset of this data field in glibc. And that's the reason why I was saying that perhaps you may need to have the libc's base address in the future. Because if the library is dynamically linked, then it means that you will need to get the absolute address during execution. So that's why after you get the offset of those data fields, you also need to know the runtime base address of libc, and then you add them together, you will be able to get the runtime absolute address of those fields. All right. Okay. If there is no questions, let's start to work on today's challenge. Same IP, different port, and then similar to before, we have 4 files ready for you to download. And the libc base address in the server is this one. And then notice that this will be different from the one that is running in your local. And you need to figure out the libc base address by yourself in your local environment. And I also recommend you turn off ASLR by the time you run the program, because in that way, you will be able to have a fixed libc's base address. Okay. All right. Yeah. Now is 11:17. I am going to give you, say, yeah, we probably don't have too much time. Hopefully, I'm giving you like 8 minutes. So it's like starting from 11:25, we will start to work on this challenge together. All right, let's work on this together. Okay, so we're gonna just follow the step that we talked about from the slides. The first step is that we want to kind of like find a hypothetical fake chunk, right? And as we mentioned, we want to find, where, say, malloc is at, so that we can use that as, part of the fake chunk. Basically, it's going to become the data part of the fake chunk, right? Okay, so now let's first figure out where the where the malloc is. Sorry, my brain just stopped. Okay. So let's do upstomp dash uppercase T, and then libc dot so dot 6, and then grab malloc. It's actually underscore malloc. Oops. Okay. So now we get to know this is the offset. Keep in mind that this is offset, right? Because libc will be linked dynamically, and then this is the offset that we get from it. All right. I am going to actually take a note here. Malloc this one. Okay. All right. Okay. Then now we have this hypothetical address. Let's start to run this program. I'm going to use GDB. And I'm going to run it. Okay. And then I'm going to set the interaction there because I want to look at if I can access this correctly. So I need to look at my current base address. And the reason why I am, looking at the base address in this process now, instead of using the base address dimension from the slides, is because when you use GDB to run the program, the base address will different from that you run the program directly locally. Okay, so that's why if you use GDB to run the program, you need to get the base address from GDB directly. Okay. And I am trying to find libc space. Okay. So this is the base of libc. All right. And I am going to just write down here. Oops, this might be a little too small. And I am going to do a quick math. All right, so this is malloc hook runtime address. All right. Awesome. And now let's try this address. See if this is correct. Yes, it is correct. It tells you that this is malloc hook. Okay. Okay. Next, what we're going to do is that we'll continue to run this program. Okay. And we are going to come up with this kind of data structure, right? Because we want to use Fastbin, use after free, and in order to do that, we need to first have something in Fastbin so that we can use it, right? But then in order to have some free chunk in Fastbin, we know that we have to fill up Tcash bin. And that means that there are going to be at least 7 items here, right? So we need to fill up this Tcash bin and also have one more chunk in Fastbin. And in order to do that, we need to first allocate, say, 8 chunks, and then free them all so that we're gonna have this layout. Make sense? Okay, so let's start to do that. Malloc, okay, 1 time 2, 3, 4, 5, 7. Wait, I forgot 6. This is 7, 8. Okay, and then now I'm going to list them. Okay, good. Now we have 8 chunks, right? Numbering from 0 to 7. And then next, I will start to free them. Okay. Before that, let's take a look at the current bins. There's nothing there, which is expected, right? Okay, continue. Now let's start to do the first fray, fray 0. Okay. And then let's just end on there and then take a look at the current bins. So now we have 1 chunk in Tcash bins, right? Okay, and then I'm going to continue. I just read the next one. Okay, let's take a look. Good, so now we have 2 chunks, right? Okay, I'm going to continue. Then fray 2, fray 3, fray 4, fray 5, fray 6. All right, and take a look at the bins. Now we have 7 items in Tcash bins, right? Okay, all good? All right, I am going to continue. And the fray number 7, which is the 8th chunk, all right? And now let's take a look at the bins. Okay, so now we have this chunk goes to Fastbins, okay? So this number 7 chunk goes to Fastbins after it is freed because Tcash bin is full. Okay, good. So then the next thing, also, if there's any question now, feel free to ask me. If there's no question, I'm going to continue. Okay, so the next is that I want to start to change this bin's information so that I can make this bin to point to my hypothetical fake chunk, right? Okay, and before we do that, let's take a look at the value stored here in those bins, okay? So if we list the current pointers, okay, so those are the pointers value, means that this is going to be the address of where the data starts, right? So that's not the start address of the chunk, it's the start address of data, okay? Keep this in mind. And also, let's look at the values that are stored in Tcash bin's free list and Fastbin's free list, okay? So those are 40, 52, 60, 80, and then A0, C0, right? And then those are the same as the start of data, right? Okay, but then let's take a look at Fastbins. And that one is 330, right? So that value is associated with the last chunk, but the address is not exactly the value of this pointer, right? And this is because 330 is the start of the chunk, whereas 340 is the start of the data, right? Okay, good. So keep in mind the difference. And now we are going to construct this fake chunk. We want this fake chunk to have the data that starts at this location, right? So that means that the chunk should start with this minus hex 10. So that's going to be the address that ends with FC20. Make sense? Okay, good. So now it means that yes. Oh, because this is the address of malloc, okay? And we want to make this address become the start of the data, right? And because of that, the start of the chunk has to be FC20 because the metadata, which is the start of the chunk, will occupy for hex 10, which is 16 bytes. Make sense? Awesome, cool. Okay, so now we know what we should do. So we need to make sure that in this location, right, it starts this minus hex 10 value. And because of that, we need to use this command, but this address cannot be converted to a typable string. So I'm gonna just use GDB to directly, access that memory location and change the value. But if you write your Python script, you can make that converted to, a byte stream and send it to the server, right? So this is similar to what we did from last time for the Tcache attacks, all right? Okay, so now I am going to set this guy, right? And then equal to this value. And I need to specify that I want to, write for 8 bytes instead of 4, because by default, it will consider this as a 4-byte integer. All right. Okay, so let's take a look at what will happen the next after we change this. All right. So now, if you look at the Fastbins, right, you will realize that after the original one chunk, we have another next chunk, right? So, which is similar to what we did here. It's just like there's no, this 2 chunk doesn't exist because the FD pointer will be equal to 0, 0, right? Okay. So now we have this fancy layout, and then you will realize that it says something, right? Like it says memo line hook, and it's okay. We don't really care about that. The reason why it says memo line hook is just because this address is another symbol in glibc, but we don't really care. All we care is that this address is 16 bytes ahead of malloc. Okay. All right. So now I'm going to pause here a little bit because I need to do one more thing, which is to change, the use of malloc to free hook. And I will explain to you guys later on for why I'm doing this. But now just like, forgive me, I'm gonna change it because I know that I was using malloc as an example, and I said that free hook is also usable. But then in some situation, depending on the service, depending on the vulnerable program that you're interacting with. In this case, we cannot really use malloc, which I will explain later, right? So, but then interchangeably, I'm gonna use free hook for now. So I'm going to redo the math and then change it. Okay. So op sum -t, libc, grab free hook. I get this guy's address, right? And then I am going to get this and the libc space, plus them, sum them together. Okay, which is this value. And this is going to be free hook. Cool. And then I am going to change this to this. Okay. And then let's look at the bins again. All right. Oh, you know what? I forget. I need to make this minus. That's the right. Just keep in mind we need to let it point to the start of the chunk, not the start of data. Start it again. That's right. Yes, I'm very bad at math. Thank you. Thank you for correcting me. Cool. All right. Now we make it pointed somewhere, right? The hypothetical chunk. And then now let's start to malloc them, meaning that we're going to take out those chunks. Okay. All right. So I'm going to continue. Malloc. Okay. Remember that I do malloc for one time. And let's take a look at the beans. Okay. So there's 6 elements in Tcache beans now, right? Because we just managed to get 1 element out. Okay, let's continue. I'm going to do malloc 8. 2 times 3, 4, 5, 6. Okay. There should be 1 element left. All right. Do it again. Okay. Okay. No element in Tcache beans, right? Okay. Now we're going to do this. We're going to have our life change moment. We're going to malloc again. Okay. So the chunk goes to Tcache beans. And let's look at the current ender use pointer. And you see that they are the same as what we have here, right? Okay, good. Now let's do malloc again. Nothing there, right? All the chunks are currently in their use. And see, the last chunk is what we want, right? And that's the value of it is the same as the value that we specify here for free hook. Awesome. Then the next that we need to do is to change, get this pointer, add this pointer's value. So replace this to the address of function win, right? And then we call free again, and then we will actually go to win. Does it make sense? Okay. So yes, question. Okay, yes, I will come back. Yes. So question is, okay, now let's talk about why are you using free hook, not malloc hook? So the reason for that is because, malloc, it looks like there's only malloc, but it turns out that for gDeepC, there are many, many places that call malloc internally. For example, gDeepC's puts function will actually call malloc. And the reason why I avoid using malloc in this case is because if you look at my program, the service, I think in the win function, I have printf, this guy. And for printf, if there is no format string specified, then printf will be converted to put. And the put will call malloc. So if I change malloc to function win, we're going to get stuck here. There's no way that you can go to the rest of it to let you open the file, to write the file, blah, blah, blah. You will always you call win goes to printf, which is put, and then put calls win, and then, hey, you come back in here again. Right? So there's no way for you to finish the rest of the operation. So that's why I'm avoiding using malloc hook in this point. And also that's another interesting thing is that if we're using free hook, actually For F close, it will call free, which will goes to free hook. And that's why if you manage to attack this vulnerability successfully, you will realize that it asks you for printf, like it asks you for ASU write ID, and after you type it, it will ask you again. Because like by the time that the function, the program execute F close, it will then call free, and then free will call win, and then you come back here again. So that's gonna be an infinite loop. Fortunately, it's not gonna affect you. Yeah, don't be scared about that. Fortunately, you will still be able to log yourself, even though that the file is not properly closed. So it doesn't really affect you from logging, but then that's why you will see, you know, this match just keeps popping up. And all you want to do is just to terminate this process by yourself, terminate the communication by yourself. Okay, cool. So yeah, that's for today's lecture. I am going to see you guys next week. We leverage the pointer to what? Yes. Yes, exactly. Because in that case, it will fall free, and if free goes to free, which is something. Yep.